If we think about reactions that happen in the gas phase, so all of the reactants and products are gases, sometimes it's easier to measure the pressure instead of the concentration. And so we do have a relationship that allows us to relate the concentration of our gases to the pressure. And so if we are finding an equilibrium constant for concentration, we call that Kc. If we're finding an equilibrium constant for the pressures of the gases, we call it Kp. And they are related to each other. The way that they're related to each other has to do with the ideal gas constant R, and in this case it's the 0.08206 because we're dealing with pressures, and the temperature, and that temperature does need to be in Kelvin. We're also going to have to consider the number of moles of gas of the products and of the reactants. So we take the products, moles of products, minus the moles of the reactants of gas. And that is our exponent for this ideal gas constant temperature ratio. So our Kp, the equilibrium constant with respect to pressure, is equal to the concentration times RT raised to the difference in the number of moles of products minus reactants. So let's try an example. If we're given the equilibrium constant for pressure for a reaction of nitrogen monoxide and oxygen forming nitrogen dioxide, we want to find the equilibrium constant for the concentration. So we do need to find the difference in the number of moles. So if we take products, so we have 2 moles of products. We have 2 plus 1, so 3 moles of reactants. We end up with a -1 for the change in moles of gas. So our equation is Kp equals Kc times RT raised to that change in number of moles. We want to rearrange this to find our Kc. So we get Kc is equal to Kp divided by RT raised to the number of moles, the difference in the number of moles. So now we can plug in our values. So our Kp was given. R is the ideal gas constant, 0.08206. And again, we're using this because of the pressure, so the atmospheres. We have to multiply by the temperature in Kelvin. So we need to take 25 plus 273, and we end up with 298 Kelvin. And we need the difference in the number of moles, which we found was a -1. Okay, so if we're raising something to the -1 power, that is the same as 1 over, so the inverse. So when you're multiplying this out, you have to take the inverse of the ideal gas constant times the temperature. So we end up with a value of 5.4 times 10 to the 13th. So this does show us that we have an equilibrium constant that is larger than 1, and so we're favoring the products in this particular chemical reaction. And we've now found the equilibrium constant with respect to concentration when we were given the equilibrium constant with respect to pressure. So here's two for you to practice. Pause the video and see if you can either find the Kc or the Kp for each of the following reactions. So we're given Kc in this case, so we want to calculate for pressure. So we can plug in our equilibrium constant for concentration. R is our constant, 0.08206. We do need the temperature in Kelvin, so 27 plus 273 gives us 300. And we do have to find our change in moles. So we had 2 moles of product, and we have 2 plus 1, 3 moles of reactant. So 2 minus 3 gives us a -1 for that exponent. So our Kp in this case is 3 times 10 to the 24th. Okay. All right, in our next example, we're given Kp. We want to find Kc. So we rearrange the equation. We're at the same temperature again, so now we can plug in our values. R is our constant. Times the temperature, which again is the same for both of these. That should be okay. And change is 2 moles minus 3 moles, so we end up with a -1. We don't always end up with a -1. It's just these particular examples. They were all 2 moles as the product and 3 moles as the reactant. So if we do our calculation, our Kc is 7 times 10 to the -16th. So we're much smaller than 1, which means we're favoring our reactants.